Well, hi there, sports fans. Welcome to another edition of Physics 12, Lesson 2.1. Today we're going to introduce the topic of forces, and you will be hearing about this for the rest of the year, actually, because that is basically what we look at in physics. We look at forces. And I'd like to start out just by saying we don't really have a very good definition of a force, because a force really is just defined as the push or pull on an object. And so that's about as good as it gets right now as far as a definition of a force. That may change as we learn more about, from the Higgs boson and things like that. And we might have a better understanding of forces and how they originate, why forces exist. But for right now, that's about as good as it gets. A force is just simply a push or a pull on an object. So we have a number of different forces that we will be looking at in this course, and so we'll look at those right now. First of all, we have the force of gravity, which you've had some experience with, obviously. We use Fg, the symbols Fg, to represent the force of gravity, and obviously this is due to the mass of the Earth. Any two objects that have mass, they will actually produce a force of gravity on each other. And so the force of gravity is just simply due to the mass of the Earth, and it is the direction of it would be toward the center of the Earth. All right, so that's why it's always down anywhere you are on the Earth, because it's right toward the center. We also have a friction force that we will be dealing with this year, and this is friction forces are due to uneven surfaces between objects. And it doesn't matter how smooth you can make a surface, there will always be, if you get right down to the level of the molecule, there will always be uneven surfaces, there will always be tiny ridges, even if it's the size of molecules. But it doesn't matter how smooth you get things, there will always be a friction force. Having said that, if we imagine our world without friction, it would be a totally different place. Friction is a source of waste energy, of course, always, just about anything that moves. But it's also, we've made very good use of it in that it makes it a little more convenient for getting around too, actually. So if we actually didn't have friction, our world, just imagine, our world would be a totally different place in the way that we get around. Friction, it will be opposite the direction of motion. So when you determine the direction that an object is moving, the friction force then will be opposite that direction. We also have what's called a normal force. I'm not sure if you looked at this last year in the physics course or not, but the normal force is that force which it's usually the force that holds up an object. For example, I'm on the second floor of this building here right now. The reason I don't fall down to the first floor is because the floor that I'm standing on is providing a normal force in the up direction, and in this case it's equal to the force of gravity, and that's why I'm not moving at all, or I'm not accelerating in the y direction, and that's why I'm not falling down to the first floor. The floor that I'm standing on is producing a normal force which is equal to the force of gravity, and so I remain I have no motion and no acceleration in the y direction. This, generally speaking, it is in the opposite direction of gravity, but not always. There are some other cases, like for example, from a wall and things like that, and we will look at those things later on. We also have tension forces that we'll be looking at, and this is mostly from a pull from a string or a rope that's attached to an object that we'll look at. Remember, you can't push an object with a string or a rope. And so a tension force, generally speaking, will be a pull on an object through a string or a rope. We also will be looking at what we call applied forces, and this is just some kind of external force that's applied to an object, usually from a person. You're pushing on something. So we refer to that as an applied force. We usually don't actually put the APP on there. And so an applied force, if you just see an uppercase F referring to a force, then you can assume that it is an applied force. and it comes from some external source. We'll also be looking a little bit, we won't go into this in too much detail, a drag force. This is due to air resistance. And this actually gets a little bit more complicated because it actually varies with the speed of an object. So it's not, the force is not constant. And so that gets much more challenging to deal with. And so when you're dealing with drag forces like that, then you need a little bit more advanced calculus in order to analyze the motion of something with a drag force. So we'll be looking at it a little bit, but not too much this year. Then that leaves me with the net force on an object. So this symbol right here refers to the sum of. So it's a sigma symbol, and it refers to the sum of all forces. So that will be the net force. So when you look at all the forces in the x and y direction, you total them all up, and then you determine what your net force is in the x direction and the net force in the y direction. And that will determine the acceleration of the object that you're analyzing. So those are the types of forces. And so you will be seeing this the remainder of the year. F net equals ma. So in other words, the net force on an object, when you total all the forces that are acting on an object, that will equal its mass times its acceleration. So when you know all the total forces on an object, then you know how it will be accelerating in the x direction or in the y direction, or both. So how do we do this analysis? And we do this with the use of what we call a free body diagram. Again, going back to the diagrams. And your diagrams, I can't overemphasize how important a diagram is. So let's look at how we make these free body diagrams. So we'll start with an object that has some kind of a mass m. And the first force that we'll look at is the force of gravity. So obviously that's in the downward direction toward the center of the Earth. And that equals just simply the mass of the object times g, which is 9.8 meters per second squared. So that's how you determine the force of gravity on an object. And again, it's just the mass times the 9.8, and it's in the down direction. So that's a gravity force. Then we have force of friction. You also want to put on your diagram the direction that the object is moving. So just put the direction of motion on there. And then your friction force will be in the opposite direction. So if an object is moving that way, then obviously the friction force will be in the opposite direction. So that's a friction force. And then we have, again, here's the normal force. And you might not have seen that before, I'm not sure. But again, in this case, it will be in the opposite direction of the force of gravity. And in this case, too, it will be the same as the force of gravity if you're not having any acceleration in the y direction. So to keep the object still, like I'm just standing here on this floor, then the normal force in the up direction will be equal to the gravitational force in the down direction. So that's a normal force. And then we have, there's a tension. And again, like we said, you can't push on a string or a rope. So tension, if you have a string or a rope attached to the object, then it will be in that sort of direction like that, the tension. Then we have the applied force, and I put the APP on there, but generally speaking, you won't see that. So you'll just have an uppercase F that refers to an applied force. So there's your applied force. And I just put this on here because the drag force doesn't really pertain too much to an object like this. But you see that more in terms of, like for example, if somebody in a parachute, you have the drag force from air resistance will be in the up direction, and so that's what's slowing the person down and preventing them from hitting the ground too hard, obviously, with the parachute. And as I said, the drag force, it will vary with the speed of the object, and that's why it gets a lot more complicated. And then, so that brings us to, once you've got all the forces on there, and in your analysis, you'll be given what forces are acting on an object, or you might have to determine that. but in any case, the net forces that are acting on the object will equal its mass times its acceleration. So that's how you will determine the acceleration of an object. So here this object has a mass m here, and so when you total up all the forces in the x direction and the y direction, then that'll give you the acceleration of the object. And I just want to just add to that when you know the acceleration of the object, then you want to put that on your diagram as well. So put your motion on there, put your acceleration on there, all of your forces, and then in the end of your analysis you will know what the acceleration of the object will be in the x direction and the y direction. So you need to, once again, move this up here, you need to separate the forces in the x direction and in the y direction, and then you'll be able to determine what the acceleration is, if there is any in the y direction or in the x direction. So we will be looking at forces pretty much the remainder of the year. And once again, the crucial part of this is getting your diagram there, getting all your forces on there, and that'll take you a long way into being able to solve these kinds of problems with forces and determining acceleration of objects and their motion, etc.